Welcome to ChemDoctor, and in this presentation what I would like to do is explain to the viewer how atomic size changes as we move down any particular group on the periodic table. Now, when we talk about atomic size, here's the thing that you need to remember. It's going to be basically dependent on two things: the force of attraction that's being exerted on the surface electrons by the protons of the particular atom in question, and how far away in terms of distance those surface electrons are. And so we have sort of two competing events that are going on when we move down any group on the periodic table from one element to the next. And so what we need to do is break this down and look at the two competing factors. In order to do that, we need to talk about Coulomb's law a little bit. And basically what Coulomb's law says is that the force of attraction, right, so the force of attraction on the outer electrons or the surface electrons is going to be in proportion to, and I'm going to keep this very, very simple, it's going to be in proportion to the charge that's available to pull on those outer electrons divided by the distance those electrons are away from the protons, quantities squared. So the charge available to generate a force of attraction on the outer electrons versus how far away those electrons are from the protons, quantities squared. This squiggly here means in proportion. So I'll abbreviate that here. So in proportion to. So the force of attraction, how hard the protons are pulling on the surface electrons, is going to be dependent on the charge available to generate the force of attraction divided by the distance squared. Now just think about this for a minute, because the protons and the neutrons, which are in the nucleus of the cell, represent a very tiny part of the atom that has over 99% of the mass. So the protons and the neutrons are not involved in determining the size of the atom. It's all about the electrons, and in particular the surface electrons, how far those valence electrons are away from where the protons are will determine how big the atom is. Now in this case we're going to be investigating how the atomic size changes as we move from the top of a group towards the bottom of a group. Alright? Now there's another aspect of this. Over here on the right side of the screen, I have written a schematic that relates the distance of a particular energy level away from the protons by comparison to the potential energy of those electrons and ionization energy. This diagram appears in a lot of the videos that I produce, and we're going to use this right now to rationalize what's happening with distance. The other thing that we need for this, the other concept, is a concept called effective nuclear charge. And this is going to be equal to the number of protons, which represents essentially the total protonic charge, minus the number of what we call core electrons. And in a way of thinking, the effective nuclear charge can be thought of this way. It's the charge available to exert the force of attraction on surface electrons, on the surface electrons. So what we're going to do, we're going to start with lithium, and coming back up here to Coulomb's law, what we're going to do is we're going to focus on the two aspects of this fraction. So the first thing is that we're going to talk about how the charge is changing as we go from lithium down to potassium, and then we're going to talk about how the distance changes for the surface electrons as we move from lithium down to potassium. So like in some of the previous videos, what we're going to do first is generate the electron configuration for a particular atom. Alright, so we're going to look at lithium first. It's got 3 electrons. Its configuration will be 1s2, 2s1. All right, and I'm going to remind the viewer that, and I'll underline it, this is our valence. So this electron here is actually our surface electron. And what we're going to want to do here is try to figure out or generate some kind of a conceptual understanding for how hard that electron is being pulled on. And the way we're going to do it is by calculating the Z effective for this. So the Z effective is going to equal, all right, it's the total number of protons, of which there are 3. And then you can see, as I've spoken about in previous videos, that the 1s2 electrons here represent what we call the core. So I'll go ahead and circle this. And these are core electrons because they sit between where the protons are and the surface electron. And they operate in terms of what they do by screening some of the charge that's in the nucleus away from basically the charge that's available to pull on the surface electron here. So when we calculate the Z effective for this outer electron in lithium, it's going to be 3 minus 2 or plus 1. And I'm going to go ahead and write that down up here next to the lithium. So my charge available to generate force on that surface electron is plus 1 for lithium. Now let's move down to sodium and talk about what's going to happen with this one. My configuration here for the sodium outer electron is going to be 1s2, 2s2, 2p6, 3s1. And again, I'm going to go ahead and I'll underline my surface electron. All right, so this is the surface electron, or the valence, depending on how you want to look at it. And our core now is going to be here. Because all 8 of these electrons, or excuse me, all 10 of these electrons, ChemDoctor needs to work on his adding. All right, all 10 of these electrons are screening a certain amount of that protonic charge away from this surface electron. So my Z effective for the outer electron of sodium is going to be 11. This is the atomic number of sodium. All right, this is the number of protons that we have in the nucleus, minus the core electrons, which are 10, and that's going to leave us with plus 1 again. All right, so this is significant because as we move from lithium down to sodium, you can see that what happened to the charge available to generate force of attraction on this surface electron remained constant. So as we went from lithium to sodium, and I'm gonna just go ahead and extend my fraction bar here, the charge remained constant. Now, just to drive this home, let's go ahead and calculate this for the potassium. All right, and potassium's got an atomic number of 19. Its configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, its surface electron is here. All right, and that means the core for sodium is this whole bit, which happens to be 18 electrons. So the Z effective for the potassium is going to be 19 minus 18, or, as you have it, plus 1. And so you can see as we move down any group that the charge that is available, I'm going to go ahead and expand this here, even though I've written it here, charge available to exert force on the surface electrons. So this is charge available to exert force, all right, is constant. So I'm going to go ahead and put that in the top of our fraction up here. So now what we need to do next is investigate what's going on with the distance issue. How is the distance factor affecting this surface electron as we move down the group, right? So for lithium, I'm going to go ahead and put in the electrons for lithium. So we have 1s2, 2s1. All right, and so we see that the surface electron, I'll put an asterisk by it, is out here in energy level 2. The distance factor for that is going to be this. All right, Now let's go ahead and do sodium next, and we can go ahead and fill in. I'll use a different color for the sodium, and its surface electron is going to be up here in energy level 3. So look what happened here. Let's see, maybe I can squeeze this in some way. I'll use red again. So my distance factor for the sodium electron is here. You can see there's a substantial difference between lithium's surface electron and where we find sodium's surface electron. So our distance factor is increasing substantially as we move from lithium to sodium. So the distance is going up substantially. I'm going to put an up arrow there to emphasize this fact. All right? And then when we look at potassium, we add in its electrons. I'll change the color again. You can see that its surface electron is here in energy level 4. So once again, the distance factor has changed substantially as we move from sodium down to potassium. There's a significant difference between lithium and potassium. I mean, look at this. I mean, granted, this is just a loose diagram, but look at the difference. So our distance factor has increased a lot. So let me go ahead and we'll write this in now. All right, so now as we move down any group on the periodic table, you can see what's happening. The charge that is available to pull on that outer electron remains a constant value moving down any group. So it's not going up, it's not going down, it just remains the same. However, the distance factor is going up significantly as we move down the group. And remember that the force of attraction is calculated by dividing this number, which is a constant, by the distance factor squared. So our force of attraction is going to decrease. I'm going to write this down. Force of attraction decreases as we move down the group. So the force in which the protons are pulling on the surface of the surface electron is decreasing substantially, becoming weaker as we move down the group. And consequently, and this is the clincher right here, size of the element, of the elements, increases, moving down any group. All right, and with that, I'm going to go ahead and close this video.